Maybe it's a good time, by the way. I just want to mention, I want to just at least get you guys to start thinking a little bit about your final projects in this class. So I haven't given you the handout for it yet. It's scheduled to get released in Moodle, I think, in a week or two. But the basic idea is you're going to do a video presentation, which isn't that different than the ones that you guys have gotten used to doing. It's going to be somewhere on the order of 10 minutes long, nothing terrifying. But what I want you to do is consider something either in the past or something that is in the future at the edge of what we know, where the story that we're telling about something in the solar system is changing or has changed. And I want you to you're going to have to go and do a little bit of research and find some different articles that are pointing to that change as it happened. Say, like if we were talking about, well, as we go through the class, I'll point them out as they happen. I'm going to be mentioning several of them. I've already mentioned several of them along the way, but I want you guys to focus on these moments where the scientific consensus has completely redirected and where it could be redirected potentially in the future to some of the things that are changing in the way we think about stuff. So as we start to go through these bodies in the solar system, you're going to see that people have had all kinds of crazy ideas about these bodies, and that there's a lot of crazy ones that people are proposing right now. And so I want you guys to start to keep an eye on those, write them down as we come across them, because those are good topics for you to investigate for your final project. So let me ask you this. Somebody tell me what science is really quick. Yeah. Come on, give it a shot.
Is a observation proven mathematically.
Interesting. Proven observation, mathematics. Okay. Anybody else? Ideas? Yeah. Can study. What do you mean by studying? Okay. So there's like something systematic about it. I see that. Systematic. Study. What did you say? Observations too? Yeah, I'd say observations are involved. Mathematics. That's interesting. Math is really good for cataloging what you see, right? So part of the study thing, I think. Any other thoughts about science? Don't be shy. Come on. You guys didn't get food poisoning last night. That's all.
Say having a question about something, getting a hypothesis on how you think it works, and then testing and retesting based on the results.
Yeah. I think that's very close. Question that you asked. So you want to know how something works, usually something about nature, right? Something natural. Usually when we're trying to figure out how something like a computer works, it's like engineering, right? It's kind of different, similar, related, but science is generally, we're looking at something in nature, trying to figure out how it works. So we have a question about it, right? Like, how does light work? How does this flashlight make light? Okay, good question. And then the hypothesis thing is interesting too. So you brainstorm some ideas about what all the possible solutions could be. And then ideally, what you do is you knock down those possible stories, right? You try to talk yourself out of them. And so what I'm trying to get you guys to see is that as we've gone through the history of science, which has really only been a couple of 100 years, people have taken all of these wild ideas and they've pared them back. They're really constraining the set of possible explanations for things. So, where did we'll be talking about the Earth first. Like, why are the continents shaped the way they are? Okay, good question, right? It's a good scientific question. And so people have a bunch of different ideas, and two of these ideas become very popular, and they kind of go to war with each other head on, right? And there's lots of arguments for each one of these hypothetical explanations, right, that constitute a theory. There's pieces of it that are hypothetical still. There's hypotheses embedded. And both of them kind of set to war trying to figure out if they can tear back the other one. And so we see that kind of story play out over and over and over again. And I want you guys to just keep an eye out for it, because that's at the heart of what I want you to analyze for your final project in this class. Have you guys ever seen this picture before? It's kind of nuts. This is all of the space missions that we've sent out into the solar system. So this is Earth, all little tendrils reaching out into the distance. And I like this picture because it almost gives you this feeling like the Earth is some sort of, almost like a, has like roots or like a tree-like nature to it, right? We seem to be branching out, and I think that word branching is appropriate. So we've gone to the atmosphere of Jupiter. We've landed on the surface of Venus, Mars, the moon, Saturn's moon, Titan. We've been in Saturn's atmosphere at this point. By the way, this is all the way up to 2015, this image. So we've been to more places since then. Basically, we're getting out there and we're getting after it. And by going out there and getting after it, getting all of these robotic projects sent, we can actually start to constrain some of the stories that we're telling about these projects. The telescopes help us do that too, because this is the first time in human history, really in the last 10 years, that we've been able to look at other solar systems besides our own. That's crazy because, as you're going to see, the story that we've been resting on for our solar system was concocted about 300 years ago and hasn't really changed too much since then. So we're really starting to change our stories about these things. So what's included in the solar system? This might seem like a trivial question, but I would hate for you to leave this class and not know the answer to that. Anybody? What's in the solar system? What's not? Yeah, please.
Sun,
Yeah, moons. They're rings, asteroids, comets, bunch of dust. Okay, cool. That is essentially what we're constraining this class to. Now, the funny thing is that as we catalog all of these things, what we really want to do for some reason as human beings is to come up with a big story for how this thing happened, how this solar system happened, which turns out to be a much more difficult project than it seems like on its face. And so today I'm going to try to crack open that story for you guys and just kind of let it simmer over the course of as we go through all these different planets, because I want you to see how that story has problems in it and problems that have perhaps solutions that are starting to develop at the edges of what's known. So, okay, let's take a little inventory here. We have the terrestrial planets. Those are the planets that are closest to us, right? So us, Venus is interior to us, Mercury is interior to that, and then Mars is right beyond us. And all of these planets, I don't want to say that they're made out of the same stuff, but they don't have huge gaseous or liquid envelopes, right? They don't have huge atmospheres. And so we kind of group them together. Of course, they're also separated by this strange asteroid belt from the next two planets, and actually the rest of the planets, which are all could be kind of bin together because unlike us, they have these huge liquid gaseous atmosphere things. It's actually bizarre phases of matter under intense pressure that's hard for us to relate to here on Earth. But they're huge. So we call them the gas giants. We call them the ice giants beyond that, basically giant planets. So, and then beyond Neptune, beyond those giants, we have a bunch of weird little objects, which includes Pluto, and which obviously lost its planet status, and people are sometimes fighting for it to be a planet again and so on. But there's a bunch of these little things. Are you fighting for Pluto to come back? You're like, yes, you can do it. Yeah.
Can you theoretically fly through a gaseous planet?
No, it's a terrible name for it. Yeah. They're not gaseous, I'm not sure that we'll get to them and we'll talk a bit about what their composition is like. I'm gonna, we'll have enough time to spend, I think, a whole class on Jupiter and Saturn also. It's a very strange situation because you have so much pressure in these systems. I'm sure that at the upper limb of the atmosphere, like the visible edge, you might be able to fly through that. But once you get down pretty deep, you're talking about something much more like a liquid, actually. It's very hard for people to comprehend. It's all right. So if you take, I guess this is the best way of thinking about it. If you take something gaseous, simple atoms like hydrogen, right, or oxygen or anything, and you squish it really hard, it turns into a liquid, right? You just basically made it so the atoms can't move around very much, right? Oxygen tanks they cram a lot of gaseous oxygen into a little space, and it's basically a liquid. And the same thing's happening on these planets. There's a lot of atoms. They're all pulling each other towards each other, and they're squishing down really tight. And so it gets really weird. And at the center, it gets even weirder because often you have, well, first of all, people don't really know. They're guessing, but it seems like you have something very similar to the rocky planets at the center of a lot of these, particularly the Neptunes and the Uranuses, right? The icier of the giant planets. At the center of Jupiter, it might be some very bizarre form of hydrogen, some sort of conductive form of liquid hydrogen that's more like a metal, but it still jellies around like a liquid. So weird stuff. They're really weird planets, but they are not gases. And honestly, the ice giants are not ices either. It's more of, again, extreme pressure, cold, slurry type thing that's very difficult for us to comprehend. In terms of Earth experiences, there's nothing like that. Each one of this is kind of interesting. So each one of the planets, and even these little trans-Neptune dwarf planets and so forth, they all have a spin. They rotate on some axis at some rate. And in almost all the cases for the planets at least, they're all spinning in the same direction as they revolve around the sun, except for Venus, which is basically moving very slowly the wrong direction, which is really weird. And then you have Uranus, which is kind of turned on his side, almost 180 degrees on his side. So then we have, of course, tons of moons, which are all, Jupiter, for instance, Saturn, for instance, have moons that are going one way, and then they have a whole nother set of moons that are going the other way. So, to preview like the general story of how the story that we'll be inheriting, like in the textbooks say about the planet, about planets forming at the same time as the sun. It's very tricky to explain a lot of these very bizarre features, like things going the wrong direction and stuff like that. So we have to start thinking about the events that might have led to those changes. And that's where things get a little exciting and interesting as far as the future is concerned. So there's more to that, and we'll get to it. Another thing, the mass in the solar system. This is kind of interesting. Well, how do we know the mass of something, first of all? Anybody? Do we just take a scale out there? Yes. From density. Density is mass per volume. So you'd need to know the mass already to get the density. How would you get the mass?
That was more like a wild guess, but if you know the density, you can like guesstimate the volume.
You don't know the density because you're just looking at these things. Anybody? Come on, you guys can get this. Yeah.
Are we able to somehow see its like its gravitational effect?
Yeah.
And the distance away?
Yeah. 100%. Yeah. So all that Kepler stuff that we talked about, right? And Newton scaling Kepler's motions with this concept called mass. So they had this idea of mass before they could ever really see them very well or go there, certainly with robots or anything like that. Now we've confirmed a lot of those measurements and the way that we confirm them is with gravity too. You fly a robot by there, basically one of these space probes, and you see how it gets jerked around by the planet. And the way that its orbit gets manipulated tells you essentially how much the planet weighs, right? You find yourself in one of those escape velocity situations where you have a simple equation that only has one big m in it, and that's it, right? So we know the masses from not only just from observation since the times of Newton. We also have been to a lot of these places, at least with robots. And what's kind of interesting is that the sun has almost all of the atoms in the solar system. Jupiter's got all the rest of them pretty much, and then everybody else gets a few atoms, basically. So Jupiter and the sun have almost everything. Now things get really weird because, Jupiter and the sun are far from the densest things. And so you want to talk about density. This is where things start to get really bizarre. So the densest thing in the solar system, where's that? Yes, right, exactly. That's under your feet right now. Okay, so the Earth is extremely dense. It's basically a chunk of metal. There's some silicates and stuff too, but those could be considered metals. In fact, they often are by computer programmers. Um, so really, a lot of really dense stuff out there that is not in the center of the solar system, which is really weird because if you would have imagined that this solar system, kind of the standard story that I'm going to reveal for you today is that, there's this ball of gas, it's really heavy, starts kind of attracting itself, swirls together. The sun happens at the center of it, right? Because it's kind of where all the mass is at. Fair enough so far. But then for some reason, like the little planets just happen like where they're at, more or less. Some of them move around a bit. But why? Why would such dense things occur not in the center of the solar system? There's a really good question to ask yourself. So another interesting question that sort of puts some shade on this simple story. Angular momentum. Does anybody remember what that is? I've brought it up several times. Angular momentum. It's like the figure skater, right? It's how much spinning energy that you have, right? Jupiter's got almost all of it, actually, which is really, really weird because if all these planets and the sun would have condensed out of the same blob of stuff, you would think, first of all, that the sun should have most of it because it's got most of the stuff. Second of all, if it transferred it to Jupiter, how did it do that? So that's another interesting question, and these stories are things that people, these are the kind of little fractures that I want you guys to pay attention to, and I want you to chase down some of these because there's really interesting theories about what could and couldn't explain these going forward. There's some really interesting problems. Oops, I'm kind of getting ahead of myself, but there you go. Here's your density stuff. Where we got it? Density. Okay, Mercury is the most dense. I'm sorry, I lied to you, but Earth isn't far behind. Wait, no. I was right. Yeah, Earth is the most dense. Mercury is right behind Earth. They're not in descending order, which is a little frustrating. Now, an argument could be made that the sun is really, really dense at its interior, deep inside of its interior. Okay, maybe. It might be. This is also like not totally satisfying for the question of why we have such dense stuff out here because, again, if the sun sorted itself by density, why didn't the things that are 5 grams per centimeter cubed density, like the Earth, why didn't they end up, several miles inside of the sun in the first place? It's very interesting and bizarre. We'll play with some of these ideas. I'm just kind of previewing the next few weeks for you guys about some interesting gaps in our understanding that we're going to try to play with. So this is obviously the density of the sun. Theoretically, as you go, let's see here, down into it, or up into it, I suppose. The core is over here. The surface is over here. All right. We'll go through each one of these Rockies in depth. Is there anything I want to say about them in general? Earth's kind of an interesting place. It's the only one of all of these Rockies where the surface temperatures are generally somewhere between freezing and boiling for water. This is probably why we live here, honestly. All of these other places, right? It's very rough extremes in terms of the swing of temperatures. And, it's hard to imagine that Earth wouldn't look probably like one or the other if it moved a few thousand kilometers in the wrong direction. So that's an interesting active chance that we're all thankful for. And we'll go through each one of these. Venus is very interesting because, since it spins so slowly, its day is really, really long. Its day is actually, I think, twice as long as its year, actually, because it spins so slow that it's got one side that's pretty much always facing the sun. And that's brutal. The only way it gets relief is it goes around the sun, and therefore, if you consider its rotation with respect to the background stars, it's hardly rotating at all. But it does get a little bit of change because its year is kind of short compared to ours. So, Venus is a really gnarly place. I think the first spacecraft we sent there survived. The Russians actually did it. I think it survived just a few minutes only. And they're working on one that's supposed to go back in 2030 that they hope will actually be able to transmit some information for, I think, a half an hour before it goes kaput. It's really hot and miserable on the surface. Really nasty acidic sulfuric conditions too. It's a really interesting planet. 1 second. The last thing I want to say about Venus is that it's also really similar to Earth. It has it's thought to have basically a very similar construction as far as its internal structures are concerned. It has a lot of what we think are volcanoes and magma and stuff, yet it doesn't. The biggest difference, it doesn't have a magnetic field, which is really, really weird. So we're going to talk, I think, next class about how magnetic fields work. But, they're not such different planets. They seem to be composed of similar stuff. They seem to be around the same size, and yet very, very different outcomes. Yes.
Things that they sent to the Venus.
Yeah.
Just a bunch of them. Some of them survived like a few hours.
A few hours? Really? Hold on, we gotta fact check that. We need a fact checker in this class. It's called the Venera projects, right? Venera spacecraft. And they were transmitting, you think, that whole time? From 23 minutes to 2 hours for the entire Venera, all of the Venera projects. That's not bad. That's longer than I thought. Yeah, they started this all the way back in the 60s. Yes, sir.
It's just something not working.
Yeah, can we deal with it though? Like, I didn't need to deal with it today.
Okay,
Yeah.
you should have called that number then and I would have been right here.
No worries.
Went to help desk and they just now informed me.
Yeah, it's all good. It's just locked down here.
That's
There's
normal.
Yeah.
That's normal. That's nothing to do with,
Well, my sound usually works.
Hmm?
It usually works for me. The
yeah,
sound.
but that always will say locked.
It says mute though?
It should be normal.
Yeah. So anyways, this they started this Venera project in 61.
Somebody pushed this button.
Oh,
No, it's not.
yeah, awesome. Thanks, man.
No worries.
All right, have a good one. What else? Do you know more about this Venera project? You sound like you know a bunch about it. Do you watch a documentary or something? Okay.
Like they took a picture.
It did. It took some really weird pictures. I actually had one of the scientists from NASA on my show like a year or two ago who's trying to build this next mission over to Venus. I think I'll have some notes on it when we get back to Venus in full. Venus is a really, really weird one because it seems in some sense so similar. It's really our sister planet. It's much more similar in composition than Mars, for instance, but it's so wildly different too. And not just like because it's closer to the sun. Why doesn't it have a magnetic field? That's one of the most bizarre things. And it's, once we start talking about how magnetic fields are generated, the best theory we have about magnetic fields is that it has to do with all this churning magma inside, right? And perhaps a spinning core as well. But Venus seems to have all that, right? But it doesn't have a magnetic field, so we're probably missing something important. Yeah.
Venus could have lost its magnetic fields like how Mars did.
Yeah, well, yeah, that's a good question too about Mars, right? Yeah, I think so. I think it's very possible. The question is how. Like, does it no longer have a spinning core? Because part of it is, of course, to make a magnetic field, you have to have some atoms that are charged, that are in motion, and they have to be making a particular kind of motion. And we have a really unstable one ourselves. It's constantly flipping, right? It actually seems like the core is flipping the direction that it's turning. And so yeah, we have to understand magnetism to try to compare ideas. But yeah, maybe it's depends how old we think these things are too.
We know what materials inside there for and what that how to play.
So, I didn't hear that first
part.
part.
What material is
Mm.
inside there and important, but that have a play on whether or not that material could bring forth a magnetic field or not.
Yeah, so a lot of the answer is not really, but they try to guess based on the density measurements, right? So you look at how massive something is, you look at how wide it is, and you look at the surface and you say what kind of compounds you can observe in the atmosphere, stuff that's coming out of the ground. And then you try to piece all that together and say what kind of atoms could account for those things that we can see. And that's why these missions to Venus are so important, is because they're actually going to try to get some samples, or they're going to try to actually make some measurements of what the materials are while they're there. Maybe be able to determine whether these are actually volcanoes. It's very hard to tell too. The other thing that makes Venus so difficult to study is it's completely cloudy there. So if you want to see any idea of, this is probably a better picture of Venus, because it's got this kind of cloudy appearance to it. The only way you can get a real surface picture is with something approximating radar, where you do this kind of radar penetrating image stuff. But that doesn't give you a good sense of like really what you're looking at other than solid objects. So it's like people don't know. They don't know. But we do suspect that it's very similar in composition to our planet, as far as the iron and the silicates go that make up most of this place. So it's weird. We're going to get to it in depth, though. Don't worry. People do believe, because of that density stuff, that it has this iron-rich core similar to us. But maybe it's not moving, and maybe it needs to be moving. But yeah, I wonder. That's going to be a huge thing for Mars too. Also, not really much of a magnetic field at Mars. Elon's all excited to go to Mars, but it's going to be a really difficult place to hang out without a magnetic field, because you just got all sorts of nasty stuff streaming in from space all day long that's just going to wreck you. Even the solar wind from the sun, just the basic sun light as we would think of it. But the sun, just being out in the sun on Mars without an atmosphere is a really deadly situation. So, and there's some ideas about how we could actually make an artificial magnetic field. And I want to play with those when we get to Mars too. All right, so Mars, we get out to Mars, we go past Mars, we got this asteroid belt, which is really bizarre. We will spend a day talking about the asteroid belt. So the entirety of all these asteroids that you see here, so let's talk about this. So Jupiter's got these really weird pools of asteroids that it drags around with it. It's got a leading group that's in its same orbit called the Greeks, and it's got a trailing group called the Trojans. And it's sort of any one of these bodies. Earth actually has these stable points too. They're called Lagrange points, where you basically have a nice balance between the sun's gravity and the planet's gravity. And these stuff tends to just pool there. There's also Lagrange points in front of and behind the planet. And we tend to put our satellites there oftentimes, like our telescopes that we've been talking about, our space telescopes. We'll park them in one of these Lagrange points because they can just relax there, stay virtually stationary. Jupiter has piled up a ton of these asteroids there. But in between Jupiter and all of us, Rockies, there's a bunch of asteroids. And the story for what the heck those things are doing there, again, a lot of really interesting holes. The conventional story is that it kind of is leftovers from the formation of the solar system. But there's weird stuff, right? There's a few of those. There's not much there, first of all. It's only like 4%. What was it? Like 4% the mass of the moon if you add up all of these asteroids all together. So if you guys are thinking of like Star Wars or something where these guys are like diving between the asteroids, it's not like that. There's like 100,000 kilometers like between each one of these asteroids. I don't know. Don't hold me to that. There's a lot of space between them. It's very, very sparse. So there's not a lot of stuff there. And some of them are, like I pointed out, I believe it was with Ceres. Some of them, Ceres, Pallas, Juno, Vesta, they have a really moon-like shape to them, right? They're really round. They're actually too round for them to even be explained gravitationally. So they must have some history that's deeper than just being some leftover junk from the start of the solar system. So maybe somebody wants to investigate how that idea has changed over time. That'd be cool. We'll talk about it a bit more as we get there. You guys have any thoughts, questions so far? All right. Yeah. Oh. So that's Vesta, and Ceres is right next to it with comparison to our moon. So those are two of the asteroids in the asteroid belt, right? Clearly something interesting in the past with respect to this. All right, so then eventually we get ourselves to the Jovians. These things I think are most interesting because they're so, especially the first two, Jupiter and Saturn. They are, does anybody know what they're made out of for the most part? Yeah, hydrogen and helium, right? What's the sun made out of? Same thing, yeah. So they're really, really interesting for me because they are very similar to what we would call a much larger version of them, which would be a brown dwarf. And brown dwarfs are essentially stars that aren't big enough to fuse neutral hydrogen, right? So these are really cool missing link objects as far as I'm concerned. Now, to add more interest to this story, and I don't know if I mentioned this already, but one of the craziest things this new James Webb Telescope has seen, as far as I'm concerned, is pairs of Jupiters, like 40 different pairs of Jupiters orbiting each other without a star in the Orion Nebula. So we know these things can exist without solar systems. That's really crazy and interesting. We also know that they're the same thing as a star, except they're not big enough to be a star. That's really interesting too. So, I think we have to really start to open our imaginations a bit about how these things are assembled, right? I think that it's becoming increasingly untenable to think that all these planets started exactly here and went through this story that they went through exactly. I've made the case before that at some point, the difference between a brown dwarf and a sun, it's burning, let's say, or glowing, is one atom, right? It either has enough atoms, mass, to start that nuclear reaction or it doesn't, right? So there must be brown dwarfs that spend some portion of their life as a star and spend some portion of their life because they're going to kick off all this solar wind, they're going to lose mass and they're going to go back to being a brown dwarf, right? Perhaps there's bodies that spend a lot of time going in between the two, being stars, being brown dwarfs, right? So, there's really interesting discussions starting to appear about Jupiter-like planets, about brown dwarfs, which side of, can you go from being one to being the other? Could some of these things that we assumed were just part of our solar system since the beginning, did they have whole lives as other entities in different solar systems? Perhaps, yeah.
And sun mass or ratio.
It's mass. Yeah, they're both hydrogen and helium, approximately similar kind of ratio. Yeah, it's just the number of atoms crammed in there. That's it. And that's the only difference between a brown dwarf and a sun and a Jupiter. And we see lots of we see all those three kinds of bodies all throughout the galaxy, right? We see them in our own solar system. We don't see any brown dwarfs in our solar system. We don't have any huge super Jupiter type things. We have a Jupiter. A brown dwarf would typically be, I want to say, 13 times at least the mass of Jupiter. So a really big Jupiter. But the same basic architecture. They look kind of similar too, as far as we can tell. So there's a really interesting continuum there. And I think that that's worth giving some more thought to as we go forward. And especially as we're going to spend time on the Jovians. But when we start to look at other solar systems developing for the first time, this is brand new, last 10 years, that we've been able to have actual telescopic images of other planetary disks and other solar systems. We see these Jupiters in all sorts of weird places. I just told you we see some of them who aren't even in solar systems. We see them orbiting each other. We see them orbiting their star really close to it, like at the position of Mercury sometimes. And they're orbiting so close that all of their material is just getting sprayed away like a fire hose. It's just getting cooked off so fast, right? So what happens when what happens when a brown dwarf gets all of its material cooked off, or a huge super Jupiter? right? You gotta start, these are the questions that people are just for the first time able to start asking themselves because all this data is so new, right? And it's gonna really change the kind of stories it opens up as opposed to constraining. We talked about constraining the story in science, right? We thought we had a really good story for the solar system. It was very well constrained, right, in terms of the possibility space for all of these things. But it's kind of being opened back up again. There's all these new possibilities now, So what happens if you cook down a Jupiter? What does it turn into? I don't know. What happens if you cook a brown dwarf? Maybe it turns into a Jupiter. What happens if you cook down a Neptune? What does it turn into? Right? These are really interesting questions, and we see cases where the planets are getting cooked down like that. And that's something we'd never really considered before in our models. So crazy stories. So right beyond those two, which I think are the closest kind of missing link thing between planets and suns, stars, if you will, we get into these guys, the watery, icy guys, right? So Uranus, Neptune, lots to say about them, but needless to say, they're a really interesting missing link type thing too, because one of the most common types of planets in all of the galaxy, the one we see, look at these other solar systems, is a smaller version of something like a Neptune. It's similar composition, but it's smaller. And this one also is very close, a little bit smaller than that, these things called super Earths, right? And so it's really interesting because you start to look at Neptunes and super Earths and mini Neptunes and Earths, which we have found hardly any of our own Earth-like kind of planets, but they seem to be also on this metamorphic continuum to some extent, right? They all share a lot of attributes. And so, you might ask, well, why don't we just, why can't we, what would it take for it to go from something like a Neptune down to something like an Earth? How to cook it down to that size, right? Because they do have rocky cores really similar to the Earth itself. Yeah.
They found like super Earths or like Earths that are like bigger.
Yeah, exactly.
We just haven't found ones that are like kind of our size.
Exactly. Yeah. And often those, right, the resolution's pretty poor, but it seems reasonable that those might just have a huge you run out of words with this stuff. I almost said a huge atmosphere, but it's going to be so dense that it's like a liquid. Maybe it's a huge ocean-like kind of thing. We run out of words because we don't have that phase of matter here on Earth. But really high density atmospheres / really thick oceans, right? It would look a lot like Earth, but it'd be somewhere between an Earth and a Neptune. And we call those things super Earths or mini Neptunes. Yeah.
So you're saying the atmosphere is like just like a giant liquid here?
It gets at a point where you're gonna see atmospheric stuff like nitrogen. Like our atmosphere is mostly nitrogen, right? 80% of this air is nitrogen, 20% is oxygen, trace amounts of other stuff, right? If you squish that nitrogen hard enough, it basically acts like a liquid. But maybe we just call them liquids, the easiest way to deal with it. But you get into phases of really dense gas where you start blurring the line, and the phase diagrams get really weird. They depend on temperature also, in addition to pressure. So it depends where the thing's located. At any rate, these things are big. They have lots of volatiles. Let's just call them volatiles. Liquids and gases are generally called volatiles. They have huge amounts of volatiles. That means they're subject to being evaporated by radiation pressure. You get too close to a sun with a volatile, right? Just imagine taking like a cup of water near the sun. It's going to cook off. We're lucky, again, because we have this magnetic field. It really saves our lives every single second of every day. And so we're going to have to understand how magnetic fields work if we want to understand why we're so lucky, because nobody else really seems to have that same pleasure. Jupiter has a decent magnetic field, but she doesn't have any water, so not a good place to hang out. Okay, so it's really cool. So I love these. These are, I think, some of the most interesting. I mean, obviously our planet's really interesting and everything, but I think these guys are kind of the keys. Like they're the sort of like what's the word? They're like the missing links, I think, in the stories that are evolving right now for where all of our own planets came from, and how they show that you can have bodies that look very different, but you might be just looking at snapshots of the same planet across billions and billions of different years in time. And I think that stars and brown dwarfs and Jupiters are also, there's a case to be made at least that they're also on the continuum like that. So some cool continuums popping up there with the Jovians as far as I can tell. And I'm going to keep coming back to this. So don't worry, we'll do more of this as we go forward. We will spend some time on the Jovian moons, which is cool because they are everybody. We actually just sent one out, sent a probe out to Europa, I believe it was last week, I think. There's supposed to be a huge subsurface ocean on some of these moons, and Europa is one of them. And people are really hopeful that they're going to find some critters down below the surface. So they're not going to be drilling down below the surface this time, but they're starting the project. They're starting to make plans. I don't know. It's really far deep. I can't remember what it is, but it's something preposterous. The icy shell they have to drill through is kilometers thick, very, very thick. Okay. Talk more about that next time. Oh yes, and we'll get to the ring system. You know, Jupiter has a little bit of a ring system too. That's a beautiful picture. That's from Cassini, which is from 2013. It's interesting. The ring structures are made almost entirely of water ice, but it seems to be the only one of these in our entire solar system that has such a beautiful ring structure. And people don't know if it's always been there or if it's more or less recent. I think that the projections aren't good. Like it's not supposed to stick around for very long, which is quite sad. We also, again, we see these resonances. This is interesting. There's some musicians in the audience, right? There's a couple of musicians. So you know how like the tones are essentially ratios of vibrations, like wave number ratios of one to the next, right? So a perfect fifth is something like 3 vibrations to 2 vibrations, and an octave is like 1 to 2 vibrations, right? And we see all of these musical notes appear over and over again in the solar system. That's really fascinating. I skipped over a couple, but we see them in Jupiter, right? So we see the octave with Europa. She goes around twice for each of Io's ones. So Io goes around, and then, well, I guess Europa. Europa is the 2 to 1. So she goes around twice for Io's 1 rotation, right? So every time the planet goes around, it gets a little kick from the one that's in front of it. And these sync up in these perfect ratios over and over again. And a lot of them are quite musical. The same thing we see with the periods of the particles in the ring structures of Saturn. We see a lot of these musical notes, also notes that have nothing to do with music. So this orange ring here, 3 to 2, perfect fifth, right? It's like C and G or something like that. You play music, very beautiful, solid tone, very stable, but also some weird ratios like 7 to 6, which you wouldn't see in a Western musical scale too. The people who actually were first realizing this stuff back in the 1800s, 1700s, they were losing their minds because they were obsessed with music, and they were like completely convinced that this was a sign from God, that everything was, you know, back to the almighty circle, that everything was perfectly tuned because music was the key to understanding the universe and so forth. It may be, but there are also plenty of ratios that aren't part of our musical scale as well. So resonance appears over and over and over again, which is quite beautiful. So there's we were talking last week about how Saturn's gonna tilt on its side at some point. It's not really, it's kind of making its orbit around, and we're gonna be at the angle such that we see it on its perfect side like that, so that we won't be able to see its rings for a couple of years, which is tragic. But what are you gonna do? So look at, these are Saturn's moons too. I think Saturn's a really good example of somebody. I think that we can begin to tell stories about Saturn's former past lives based on these moons. You know, it's got, look at this. Each one of these systems, these are all systems of moons. And each one of these systems is moving in a completely different way, which is so bizarre, right? It's not like it just is.
I was just gonna mention so the music of the spheres, it's like
there's a book, I thought it was like largely debunked with like how it, but yeah, that's like the
But-
theory where the planets like relate to each other in a musical way.
Yeah,
I'm
yeah.
just interested in that.
Yeah. I haven't read it. Isn't it also a like a symphony by, is it a Wagner symphony? No, Vivaldi, Music of the Spheres. Um, it's a very popular concept from early scientific folk. Kepler was obsessed with this. Very like this is an old idea, and there are resonances set up for you. I don't have a list of them off the top of my head, but the planets do have resonances, and some of them are musical notes, right? So it is true to some extent. What it means, I don't know. I mean, you have to ask yourself, why does the perfect fifth sound good to you? Like,
I think it's, well, I think part of it is cultural. I think there's a huge part of it that's cultural. It's like what we were raised to hear. As
maybe,
sound
yeah,
good.
maybe. But the fifth is, I would agree with you on almost everything except for the fifth, because the pentatonic scale, do you play music?
Yeah.
Okay, the pentatonic scale is at the heart of almost every single culture's music. They
Yeah.
have extra notes, right? Like you might have some blues notes, you might have some microtones added, but everybody's got the pentatonic scale, which is basically constructed from fifths. So it seems like the fifth is somehow like gets at our heartstrings for some reason, or it sounds pleasant. It is very, like if I was to hit any object, it's going to have some extra frequencies other than the fundamental. And the fifth is one of the biggest ones after the octave. So it's like, it is very naturally occurring and regular. Yeah, Doris, did you have a question?
Fact that some of the residents were like didn't adhere to any scale, why that would debunk the theory.
That's a good question. I think that one possibility is that things are in flux and they're changing and they will settle into a more stable resonance. I wish I could derive this for you guys, because this is, if you play music, it's probably worth understanding like what the hell is a fifth? And like the reality is like if I just strike any object like a bell or a guitar or anything, basically you get like the one frequency that shows up. Like let's just say you get a bunch of vibrations at one frequency. So like you guys probably can't see that because it's in blue. Trying to find a white one. All right. So if this is frequency on the x-axis over here, this is frequency on the yeah. This is amplitude over here. So how big the vibration is. If I just hit, a drum, it's going to have one main frequency to it, which is like this peak. But every single object that vibrates, which is to say almost every object, I would say every object, it's also going to have these things we call overtones. So a couple of other vibrations that appear. And there's less and less of them as you go higher up into the frequency space. This first one is always an octave. It's always twice the frequency of the original one. The second one is always a fifth, which is crazy. So it's always a 3-to-2 ratio, 3 of the fundamental to 2, right? So why is that? It just seems to be a feature of nature, and people have made a system out of those fifths. If you just go up on a piano a fifth, and then you go a fifth, and then you go a fifth, eventually you'll make the entire musical scale. You'll come back to yourself, and you can make the entire piano out of fifths, basically. So there's something about that resonance that's very beautiful to us. But it also seems to be a really stable pattern that just occurs in nature whenever something vibrates. And you can think about, I know planets don't seem to be vibrating, but they are oscillating over and over and over and over. And so there is something cyclic and repetitive and vibratory about the orbits. They come back to the same place year after year after year after year. There's something vibratory about that. So yeah, resonance mechanics is fascinating. People get obsessed with it in the esoteric space. The musicians, of course, love resonance. What can be said about it? I don't know. But it is fascinating to just see it appear over and over again. So I'm going to try and point it out as these different tones appear throughout, because, it's cool if nothing else. Thoughts? Questions? All right. Huge extra. So these are some of the different moon structures, ring structures. There's a huge, that's actually zoomed in on that tiny little place, which is Saturn. And there's a huge dust ring outside of Saturn too. Saturn in general just seems to have a history that's very different than anybody else's. By the way, Saturn doesn't have any Trojans, which is really weird. So Jupiter, Saturn, Saturn's smaller, sure, but not much smaller. And it hasn't managed to keep any asteroids in its Lagrange points, which is really bizarre. I actually just saw a headline this week that said it got one finally. And I was like, way to go, Saturn. But the question is like, why? What happened to them, right? You know, argument could be made, Jupiter snapped them up, but why? I mean, Jupiter's not that much bigger. So Saturn just, for me, has this taste of mystery to it. It seems to have an interesting history, at least in terms of where it's been in the solar system. Maybe it's been in other solar systems. I have no idea, but it seems to have been up to something that nobody else was up to, which is really interesting. Yeah.
Is that a lot of universe?
No, I think this is, actually don't know if that's a live photo or not. That's a great question. I took this off Wikipedia. I think it's just a schematic, actually. If it's anything, I bet it's an infrared image of the dust ring, if I had to guess. It looks like an infrared camera to me. So it's like a proxy for heat, basically.
And the one you put up earlier, Saturn, was that?
This looks optical.
No, not that one. Yeah, this one. Is that just like?
I think I would imagine that it's false colored optical, if I had to guess. It's from the Cassini orbiter. Let's see what kind of imaging Cassini had on board. So, all right, I'm gonna bore you. Oh, let's see here. It definitely had a radar imager, ultraviolet spectrograph, visible light, infrared spectrometer. So a bunch of different optical systems to look in different wavelengths, basically. So I bet they kind of stitched together a bunch of different wavelengths to get that picture, if I had to guess. Oh, yeah, that one's pretty magnificent. And I wonder if that isn't the dust ring in the background, actually. But yeah, this one's very bizarre. We're gonna look at the individual rings too themselves, and they're quite beautiful. And some of them seem to have been rather short-lived. You know, there's actual like chunks of rock in some of these that are disrupting them actively, right? They've moved a little, they somehow got bumped, and so they're carving paths in the ring systems. So I don't know. Maybe we won't even have rings around for too much longer, and we'll never know they were even there, which would be kind of something to remember. Maybe it's something that happens to these Jovians from time to time. Maybe Jupiter will start getting some beautiful rings at some point. Who knows? These are very poorly understood. All right. So then we get beyond that. We got these TNOs, our dwarf planets. So we got Pluto. Got a bunch of these. Eris, Haumea, Makmak, Gongong, Huarar, Sedna, Orcus, Salacia. They go on and on. There's a bunch of these. I think this is why Pluto lost its status, because there was many others who wanted in the club and they didn't know what to do with it. So Pluto is really far away. It's very far away. It's very cold, and so are the rest of these. By the way, there might be many more beyond this that we just can't see. Why can't we see them? It's very hard to see stuff that doesn't give off light, right? So we talk about at the very outer edge, this is, by the way, there's tons of these planets. They're not planets, but trans-Neptune objects. Almost planets, dwarf planets. There's tons of them out there beyond Neptune, right? But you can't really image these things very well. You can't see them. They don't give off light, and they're cold. So if you want to do an infrared image where you can see the heat map of something, remember, any amount of heat will give off an infrared wavelength. It gives off light in the infrared. But these objects are really cold. They're not giving off a lot of light. So they're very hard to see. Now, people think that way beyond this even, like way beyond it, like way out here, is another cloud of objects called the Oort cloud. There might be huge stuff out there too, the same size, maybe even things that are bigger. But again, it's really cold, and so can't say for sure. Um, but from time to time, people will speculate. There's still a group at Caltech that believes that there's a not giant, but a planet-sized object that needs to be found because there are inconsistencies in the orbits of the other planets, especially the outer planets, that need to be explained by an additional planet. Which is, of course, how they found. I think this was how was it Neptune? I believe it was Neptune was discovered, and Pluto just to a certain extent as well. So, we're into the real mysterious land as we get out there. They're really kind of hard to imagine how cold it is too. So I think that the temperature is less than it's like 10 times colder than Mercury. So it's like going from 500 Kelvin to 50 Kelvin. Really, really cold. They get very little light out there, and people know so little about them. Some sort of icy surface, some sort of rocky mantle, and that's about it, unfortunately. Okay, so when it comes to coming up with a story for this whole solar system, which is ultimately what we would hope to do, the biggest science question you could say, the meta science question would be, what is the story of our solar system? And in order to do that, we have to put some constraints on all the possibilities that we can tell. And one of the biggest constraints is the dating of all of these things, right? How old are they exactly? And how do you know? How do you know how old something like Jupiter is? That's really hard to say. So, one possibility with the earliest thing that people did, and I think we talked about this when we talked about the moon's formation, was you count up the craters, right? You see how often something gets whacked by a crater, and then you count up the craters and you say, well, an average rate of this many impacts gives you, and with this many craters gives you this many years. Problem is, when you do that, you end up with ages that are trillions of years old, actually. So people said, well, that can't be because, for instance, we know that the Big Bang only happened 14 billion years ago. So how can these cratered worlds be trillions of years old? So they threw out that idea, perhaps prematurely. But then people said, okay, well, we've developed this new technique called radiometric dating. And I think we talked a little bit about that, but I think it's worth reviewing really quickly, that you have these situations where a rock, when it melts, can incorporate fresh radioactive material in it, right? And that radioactive material is going to decay. As it decays, it's going to leave behind some of the parent. It's not going to decay, only some percentage. It's very probabilistic. Is going to decay. You compare the amount of the daughter decay products to the parents, and you get some predictable rates. The rate at which it decays, so you can tell how old it was the last time that it melted, right? So what we've done in order to construct a lot of the stories for these bodies in our solar system is we've taken the most conservative estimate possible, which is to say, we're not going to say something is older than a rock that we've found on it, basically. So think about that for a second. We haven't found a rock that we can date the last time it melts at a certain age, whatever it is, say for the moon, 3.5 billion years ago, is the oldest rock. The oldest rock that the last time it melted was 3.5 billion years ago. And we say, that's as old as we're willing to consider that this planet or moon or whatever it is for the most part. We do the same thing with our Earth too. So to my knowledge, there's 2 rocks on Earth that are older than 3 billion years. Somebody could fact check me on this, but I think it's right. One's in Australia, one's in Greenland, and they've both been radiometrically dated to the last time, again, that they were melted and incorporated fresh radioactive material, which is kind of everywhere, was some billions of years ago. So we end up with this date for our Earth, for instance, which is a little bit older than that, based on some theorizing. And so we constrain these dates based on what amounts to a guess about how old these things are, which comes down to how old something was the last time it melted that we found. Now, I think that's kind of the most interesting piece of this puzzle as we move forward into telling the story of our solar system, because these are really, really conservative estimates. And they're often written about, like in your textbook, the solar system formed 4.5 billion years ago. Why do people think that? Well, because they haven't found any rocks that melted longer than 4.5 billion years ago. We've also only found 2 rocks on Earth that are over 3 billion years old, period. So it's hard to find old stuff, basically. Is it possible that things could melt multiple times, right? Is it possible that the Earth could have formed, let's say 8 billion years ago, and then melted its entire surface 4.5 billion years ago? And so that's the date that we stick with? It's absolutely possible. Of course, you run up against the cosmological constraints next. And in order to kind of pick at that, we have to get into cosmology, which is next semester. But, this is the hardest piece of the whole puzzle, as far as I can tell, because some of the stories that we need to tell, if we're going to come up with a sensible story for how a lot of these planets formed, other than, well, they formed exactly where they are, which is troubling for a number of reasons that we'll get into. If we want to tell a real metamorphic story, we need a lot of time to do that. If you want to have planets spending different amounts of time near their suns and burning off their atmospheres, or you want to have planets traveling between solar systems and all of these things, it could take a lot of time, actually, much more time than the Big Bang gives us time for, right? So the time factor is really, really the biggest sticker, the biggest it's the biggest limitation on our imagination when it comes to telling stories about our solar system, as far as I can tell. Thoughts, questions? Am I making any sense at all? You're like, yeah, it doesn't matter, but we'll see. It does matter, actually, because the stories that we're trying to tell about the formation of these things, several of them are just flat out impossible. One of the biggest ones, let's just go right there for the last few minutes here. One of the biggest problems is when you do gravitational models for how a planet forms, let's say our Earth, very dense, right? I already mentioned that the Earth's the most dense thing in the solar system. And you want to say that a bunch of rocks just kind of gravitated together. Well, that's a nice story. The problem is that when you try to get little pieces of dust to stick together because of gravity, it's totally fine. You can actually do those calculations and show that little pieces of dust will gravitate together in a vacuum. Okay, great. The problem is those little pieces of dust form little pebbles. Now, the problem is when you have pebbles in space, guess what they do when they start gravitating towards each other? They bounce off each other. Exactly. So there's this intractable problem in this accretion idea about the formation of the planet and all the rocky planets in the solar system, which is how do you cross this pebble to boulder boundary problem? There's no simulation that can take a bunch of pebbles and stick them together under gravity to form a boulder. And if you can't make a boulder, how are you going to make a planet, right? And boulders are an even bigger nightmare because what happens when boulders smack into each other? You guys ever seen boulders hit each other? It's violent, right? They burst apart into more dust and pebbles and stuff. So this model that things just kind of fell together and the planets just kind of coalesced is deeply wanting. And so you need a better explanation. You need a forge of some sort. And the problem is with every model that I can put in front of you about how to forge a planet, it requires a lot of time, generally speaking, or unusual events, right? Or like star systems passing each other, planets spending more time close or farther away from their stars. But generally speaking, it requires more time than we get. And why don't we get that time? Because of Big Bang cosmology, fundamentally. And also because of this radiometric dating business. Did anybody follow before you leave? Do you understand my issue with radiometric dating? Can you just tell me so I make sure you actually understand?
Yeah, basically, so it's all dependent on the last time this, like, what is now a rock was not a rock, it was a liquid, so it was melted. And so if you have, like, I mean, we know that most of Earth's mass is actually like, I mean, in the mantle, in the core, it's like basically like a liquid.
Right.
So if all you have is the last time that stuff was a liquid, then, well, what if like, 10 billion years ago, it was just all like, what if we just had like a magma planet, then we would have no rocks left over to do this kind of dating.
Exactly. Yeah. You just can't get to you can't get to old stuff. And I'll let you guys go now in just a second, but the ocean floor, for instance, is only 200 million years old. That's weird. So we're constantly recycling the stuff on the surface. It's getting churned under into the magma, right? All that evidence is gone. If there's stuff from 1 trillion years ago on Earth, you're never going to find it. You're never ever going to find it. So this is a really interesting just blind spot that we have. We can't really tell the dates of things. And all we have is our story about the whole universe to constrain how long we have to make these planets. So I'll leave you guys with that. We'll pick up with it next time. That's something to think about.